Okay, so in this video, I want to talk about the for all statements and there exist statements. So just like in the last video, we have discussed P of n, where n is in n. So this means we are considering all the statements with one variable, that is in the natural numbers. But in general, we can actually define P of x for all x in any set A. So which means we can be given a set A, any set A, and then for each element in A, so let's say for any x in A, we can define or we can assign a statement that is P of x. So sometimes it's true, sometimes it's false. So sometimes it's always true, it's always false, or some of them is true, some of them is false. And also we can have several variables like P of xy. So this means for any given pair of variables x and y, where x is in A, y is in B, we can define a statement P of xy. And also this can be true for some xy, it can be true for all xy, it can be true like for any x you can have some y such that this is true. Sometimes for any y, you can find some x this is true. Sometimes for all x and y this is false. All things can happen. So that's why we need for all and there exist statements to actually learn about what happens in these statements. Like what are the true values of these statements? What can we say about these statements? So for example, you can look at this expression. So you can define P of xy to be x bigger than y as the statement for all xy in real numbers. So which means the x bigger than y is a statement of two variables, right? Two real variables. And also you can define all different statements, whatever you want. So for example, x squared plus y is equal to 1. Things like this. You can have all different statements that sometimes are true, sometimes are false. And what's interesting is that sometimes a statement is true for all variables in that set. In that case, we say for all x in A. We say for all x in A, we have P of x. So this means for all x in A, we have P of x. Or you can say for all x in A, P of x is true. Or you can say for all x in A, P of x, simply P of x. This means P of x is true for all x in A. What does it mean? It means whatever x in A is given, after you plug in the value P of x, then the statement is true, which means P of x is always true. I mean, whenever you say always, you have to have like a scope of that, and here x is in A. So sometimes P of x is true for x in A, but it is not always true for x in a larger set B. Does that make sense? So sometimes, so for example, x squared plus 1 is never 0 for all x in real numbers. Does that make sense? Because it's always bigger than 1. But you cannot say, but this is not true, like for all x in R, in C, like in the complex numbers, x squared plus 1 is not always non-zero because I squared plus 1 is equal to 0, right? So you have to say, if you say this is always true, then you have to claim that this is always true for x in the real numbers. You have to emphasize the scope, okay? It's only true, or it's always true for x in R, but it doesn't need to be true, and it's actually false for x in C. I mean, for at least one of the variable in the complex numbers, this is false because I squared plus 1 is 0. And probably you don't need to know anything about the complex numbers when you first learn about calculus. But my point is that you have to emphasize this A. Okay. And in the calculus, sometimes we just assume if we are not given this specific a, we assume this a is the real numbers. Okay, it's like a convention. Whenever we say for all x, we mean for all real number x. But to be rigorous, you have to emphasize what the set is. Okay, so now let me show you. So this is what it means. And in practice, we have to show a certain statement is true. But how can we show it? Let's say we want to show for all x in A, we have P of x. So the direct proof would be you assume, or no, you should say let x in A. I mean, I prefer using let x in A, or you can say assume x in A. But I usually denote assume to be like the one, whenever you have P implies Q, I would say assume P. And whenever I have for all x, I will say let x. It doesn't matter. It's just the word choice. And also you can say fix x in A, or you can say given x in A, or choose x in A. It doesn't matter. So the point is that you just choose any number, any element in this set. So this x is arbitrary. So the point is that this is arbitrary, or this is just any element, which means now you want to show P of x is true, right? You want to show P of x and you win. So the idea is that the technique you use to prove P of x is true must be universal among all the elements in A. Does that make sense? Which means all you use of x are the properties of all the elements in A. So these are you can call it universal properties, but it has a meaning in later. You just want to use some property that is true for all elements in A. So for example, if you want to show some statement about real numbers, then all techniques developed here to show P of x is true all comes from some facts about all the real numbers. Okay? So this is a technique to show a for all statements. So, but as always, this is still like you are proving a statement. So you can use all the techniques that we have discussed before, like dividing into cases, like proof by contradiction, or sometimes proof by contrapositive, but definitely not here. Like if this A is the n, then you can use proof by induction, but in general you cannot use proof by induction. Okay, if this is real numbers, then you cannot use proof by induction. Okay, so let me give you an example. So the easiest example would be just to prove that for all x in R, sorry, I don't know what's wrong with my Apple Pencil today. You want to show x squared is non-negative. So prove this. So to prove this, you first let x be an arbitrary element in the real numbers. So then you have to divide into two cases. You say x is either non-negative or less than or negative. So case one, divide it into two cases. So if x is non-negative, then you multiply x. So which means you basically you can rewrite this. You have x bigger than or equal to 0 and x bigger than or equal to 0. And then you multiply, then you get x squared is bigger than or equal to 0, right? So then you have x squared is bigger than or equal to 0, and you win. And in case 2, is that if x is less than 0, then what you have is that negative x must be bigger than 0. And also, x squared, for example, in this case, x can be negative 2, then x squared is negative 2 squared, then this is simply 2 squared. Then this is simply a square of a positive number, which you have already discussed in the first in the case 1. So x squared is equal to negative x squared, where this is positive. So in the case 1, you have proved that this is non-negative. Or actually, this is positive in this case, but it doesn't matter because you are only asked to prove that this is non-negative, and you win. So this is just proved by dividing into 2 cases. But also you can see all the things here are you are using the properties of all real numbers, right? It's not only true for this specific number 2, but it's true for all real numbers. So that's why whenever we say for all statements, we are using the properties of this set. Okay. So it's for beginners it might seems not important, but later you will realize that the importance, or like the main point of this for all statement is actually happens within this set. Okay, and let's move on. So you can do this to several variables. So for example, you can, if you are asked, you can define for all x, for all y. So the proof is similar. If you want to use direct proof, you just let some variable and move on. Okay, so now let me show you another example. So now let's show that for all x, y beginning equal to 0. So this means for all x beginning equal to 0 and for all y beginning equal to 0. Okay, this is an abbreviation of that. So for all non-negative x, y, we can show that the maximum of x, y is less than or equal to x plus y. By the way, the definition of the maximum is, okay, we define for any real numbers x, y, this is equal to x if x is bigger than or equal to y, and y if x is less than y, or you can just simply say else or otherwise. Okay. So which means if x is bigger, then this is x. If y is bigger, then this is y. If they are equal, then either one of them. Okay. So I want to show this is true. So first thing, you have to fix or choose or let x, y be non-negative numbers or non-negative real numbers, and then you want to show the maximum is less than or equal to that. So you can assume. So the point here is that you actually need to divide into 2 cases, right? Either x is bigger than or equal to y, or y is bigger than or equal to x. But here the thing is that this is a symmetric statement. When I say symmetric, I mean it is symmetric for x and y. Which means if you change x into y and y into x, then clearly max of yx is the max of xy, and then y plus x is x plus y. So the statement becomes the same. Which means if you can prove the statement for x bigger than or equal to y, then you can just do the same thing for y when y is bigger than or equal to x. In this case, we can assume without loss of generality that x is bigger than or equal to y. You can also assume that x is less than or equal to y, which means you just need to show one case, and the other case is exactly the same. So this is what it means for without loss of generality. So so the abbreviation for that is WLOG, not vlog, but WLOG. Okay. So assume WLOG that x is bigger than or equal to y, then the max is going to be just x, and then this is going to be less than or equal to x plus y, because y is by definition non-negative. So if you add a non-negative number to itself, it's going to be bigger than or equal to the original number, and you win. Okay. So this is the power of without loss of generality. Okay. I mean, if you don't want to use the word, then you can just prove it for x bigger than or equal to y, and then when x is less than y, you just say similarly, this is true, and you win. Okay. Now this is for all statement. Maybe you can just do one more example. It's not hard at all. So you can just show that for all x and y in real numbers, the maximum plus the minimum. Okay, the minimum is defined as similarly. So you just choose the smaller one. If you add the max and the min, it's going to be the sum. Okay, it's not that surprising because this is also symmetric for x and y. So first you let x, y be any real numbers, and then you assume with log that x is bigger than or equal to y. So this means the max is x, and then the mean is y. So then the left hand side becomes x plus y, and then the right hand side is also x plus y, and you're done. Okay. I think you have some ideas of proving a statement like this. Maybe I will show you something kind of different. So let me show you this way. So now let's assume, or let's fix some set. Let's call it A, okay? Let's assume A is a subset of real numbers. Now let's prove that a complicated statement, and not that complicated. So if for all elements in A we have A is bigger than 3, let's prove that for all element A in A we have A is bigger than 1. It makes sense, right? If all elements are bigger than 3, then clearly all elements are bigger than 1. But how should we prove it? Okay, so now we have to be careful about the structure of the proof, because if you are not good at the structure of the proof, it means you are not good at proof at all. Okay, so you have to know what to prove and what to assume, what to do next. Like what is the thing that you want to show in the next several steps. So here we are actually assuming that for all A in A, we have A is bigger than 3, this entire thing, okay? And we want to show that for all A in A, we have A is bigger than 1. But how should we show a for all statement? Well, we have to let. I'm so sorry about my Apple Pencil. I'll try to write slowly. Okay, so let A in A. So then by this assumption, so maybe we can call this assumption star, okay? So you can say by star, we have A is bigger than 3. You can say then, because it is bigger than 3, then it is clearly true that A is bigger than 1. And you are done. Okay, does it make sense? Because I have proved that for all A in A, A is bigger than 1, so this is true. And this is done by the assumption, so this is true. So this is how you write a proof. It's not hard, but you have to know what to write down, right? You can just say it's clearly true. It makes no sense at all. So you have to prove why it is true. And you prove it using a combination of the techniques that I have introduced in the previous videos and this video and all the later videos, or the videos in the future. Okay. So also we can, so let's also introduce the there exists statement. There exists statements. So we say there exists x in A such that P of x is true if and only if, so this is there exists x in A such that P of x is true. So this means P of x is true for at least one of the element in A. It's not too much, right? It's not a big deal. We're only asking that P of x is true for at least one of them, one of the element in A. So if this is false, then it means everything is false. Does that make sense? This is equivalent to say that P of x is true for at least one of the element in A. Let's say one of the element x in A. Let me just say one of the elements in A, okay? So how can we prove such a statement? It's definitely weaker than for all x in A, P of x is true, right? Because if P of x is true for all x in A, then clearly this is true. No, you have to be careful. If A is non-empty, so if A is non-empty, then the for all statement will imply that there exists a statement. Okay, but you can see that, I mean, usually A is non-empty, but you have to be careful. Because otherwise it becomes something called vacuously true. Let's not talk about it for now. Okay, so you can see this is not a big requirement. So if you want to show this is true, all you need to do is just to pick a special value, a special element in the set such that this is true, and you win. All you need to do is just to find a particular element such that this is true. Okay, so this is also just by direct proof. You also have all different you have all different ways to prove, but to prove it directly, the direct proof is just to pick a special value. So whenever I write there exists proof, I would say take. Okay, I would take a special value. I use take instead of let to write the proof. Okay, so the proof. So now we want to show that for there exists x in A such that P of x is true. To prove it, we can just take some special value. We take x to be some x naught in A. This x naught is a very particular element. So this is a particular element. So I said particular just to emphasize that this is different from the for all statement. In the for all statement, this x is arbitrary, which means this is any element. This has to be true for any element in A. Okay? But this only need to be true for this particular element, just this one, just one of them. But which one? You have to say which one it is. Okay, you have to take a special value. So for example, you have to take x equals 1 or 2 or 3. Or if you have some previous variables, let's say you have given a variable n, then you can take x to be n or n plus 1 or n plus 2. But it has to be a specific value. It cannot be anything or something. You have to say what it is. Okay, so this you have to take x to be a particular element, and then all you need to show is that P is true for this particular element, and you are done. Okay, so let me give you an example. So let's show that there exists some x in R such that x squared minus 5x plus 6 is equal to 0. So to prove this, you can just take x to be a special value that is 2 or 3, but you just need to take one value. Let's say we take x to be 2. Then you just need to show that 2 squared minus 5 times 2 plus 6 is 0, but it's trivial. Okay? And you win, because you just need to show one of them is true, and you win. Okay? Okay. And also, let's look at another example. So let's show that you can find some x and some y. in the real numbers such that x minus 2y plus 1 squared is less than or equal to 0. So by the way, we all know that the square has to be non-negative, so this is true if and only if this is 0. So all we need to pick is some x and y such that this is 0. So maybe we can just choose x to be -1 and then y to be 0, and we're done. So we can just take x to be, oh my god, to be -1, and then y to be 0. So then x minus 2y plus 1 squared is going to be -1 minus 0 plus 1 squared, which is 0, and we win. Okay. So in practice, the main problem is to find a specific value for that. Sometimes you just cannot find. You know that there should be some element, but you just cannot find that element. So you have to be wise to choose this element. Okay. Also, let me show you an example of like a complicated version. So still, let's fix a set. Let's say A. Now we want to show that if there exists an element in A that is bigger than 3, then we can definitely find some element in A that is bigger than 1. Does that make sense? If one of the element is bigger than 3, then one of the element is bigger than 1. Then clearly we can take the same element. But how can you write the proof? Well, let's see. So as always, so you have to assume that the assumption is true. So you assume that there exists some A in A, such that A is bigger than 3. So now I want to emphasize that if you assume a there exists statement, guess what? You can actually take some value such that this is true. Because you know this statement is true, so it means this is A is bigger than 3 for some A. You can just take a value that's called A naught, okay? So you can take, then we can take some A naught in A, such that A naught is bigger than 3. Which means we actually breaks this statement into a variable A naught and a statement about A naught, okay? This is very important. Whenever you assume a there exists statement, you can pick a special value and also together with a statement that is true, okay? Which means now, although you don't know what A naught is, but you know A naught exists. It is some element in A, and this element should satisfy this statement. In this case, it is bigger than 3. So up to this step, this is all you can do. And now we want to show that there exists some statement, some element A in A, such as A is bigger than 1. And clearly, all the information you are given is this A naught, which means you can, if this is true, then all you can do is just to choose this A naught, which means now to show a there exists statement, you want to take some value. So here you take A to be A naught, which is the specific or the particular or the special value in A. And now all you need to show is A bigger than A naught is bigger than 1, right? Because here if you want to show this is true, then you want to fix or you want to take some special value x naught and to prove that not px is true but p of x naught is true only for this value, okay? So in this case, all you want to show is not A is bigger than 1, but A naught is bigger than 1. But now, because A naught is bigger than 3, then clearly it's true because A naught is bigger than 3, so it's bigger than 1, so you're winning. So you're done, okay? So the point is that if you are given a for all statement, if you are given a for all statement, you cannot use it directly. Okay, you can only use it afterwards, right? Because if you want to show something, then you let any variable, and then you use this condition here because it is true for all a. Then you have a is bigger than 3. But if you have a there exists statement, then you can just take the value directly. Okay, you can just take the value directly. So this is one of the hidden facts that some students are not familiar with. Now, let me show you. Maybe I think it's enough for this video. I will talk about the mixed statements. Like what if we have for all and there exists and if then and maybe equivalent all happen at the same time. So what will happen when it comes to the mixed statements? How can we prove these statements, or how can we disprove the statements? Okay, I will talk about it in the next video.